Here are our solutions for assignment 2.10. We are to look at this function without a calculator. Let's consider its domain. So at first glance, we know we want to avoid division by 0, and we need to avoid negatives under a radicand. So here, look at x squared plus 16. We know that it is always positive. In other words, x squared is always greater than negative 16. So our domain is all real numbers. So there are no vertical asymptotes. There are no factors that cancel to give us a removable discontinuity. So there are no discontinuities. So it must be continuous over the same as its domain. Over what intervals does the limit exist? Well, remember that the definition of continuity requires that the limit exists. So we have our theorem that says if we have already figured out that our function is continuous, then it must have a limit everywhere. So continuity always trumps limits. If it's continuous, it must have a limit everywhere, in which case it's easy to answer question D. We know if it's continuous, then the limit as x approaches 3 is the same as f of 3. And f of 3 we can find by simple substitution into our fraction. And it looks like we'll come up with 4/5 as our limit. To find a y-intercept, nothing new here. This is simple algebra. Let x equal 0. When we put 0 into our function, we'll have -5/4. And to find an x-intercept, of course, we let y equal to 0. Y is the f of x side. So when is a fraction equal to 0? Only when its numerator is equal to 0. A fraction can only be equal to 0 when its numerator is equal to 0. And check that that doesn't also make the denominator equal to 0. And of course it doesn't here. So we have 5/3. Let me just write that as 5/3. And now to make this abundantly clear here, you could write your y-intercept as an ordered pair. If you wish, you could write your x-intercept as an ordered pair if you wish. And now we're going to use those answers from A through E to look at question F. So looking at the intercepts and what we've already figured out, can we write a convincing argument? Y function f should have some point with a y-coordinate of -1. Well, you don't need to make this graph, but again, let me make this very clear. We know we have the point 0, -5/4, and we have the point at 5/3, 0. And we know that our function is continuous between them. We don't know anything about its behavior except that somehow or other it gets from one point to the other. So if our target value, which in this case is -1, if our target value is between these two y-coordinates and our function is continuous, doesn't the graph have to cross every intermediate value between -5/4 and 0? So the concept of IVT, I think, is very simple. Now you just have to practice enough so that you can quickly write a mathematical argument. You don't have to write it in the same order I'm writing it. I will try to use some variations, but come up with a template that works for you. We can never use a theorem in a mathematical argument without satisfying the hypothesis first. So we can't apply intermediate value theorem unless a function is continuous. Do we know f is continuous? Yes, we just worked on that up above. So f is continuous over -infinity to infinity, and we have found a y-coordinate below our target. We know -5/4 is below our target y of -1, and -1 is smaller than the y-coordinate at the other end of our interval. And now I'm going to simply tack on where these happen. This is f of 0, and this is f of 5/3. So that you can easily see the x coordinates as well as the y. So you're simply saying your target fits between two y coordinates. Thus, there is at least one real number c and now we actually know where c is, so you give us your interval here. C is going to be between our x coordinates of 0 and 5/3. So at least once somewhere on this graph there has to be a value of c where we get a y coordinate of -1. So there has to be at least one real number between these two x coordinates where f of c is equal to our target of -1. And how do we know this is all true? By the intermediate value theorem. And you can just repeat that process once you get a type of argument that works well for you. All right. Question 2, we have a polynomial function. Polynomial functions are continuous everywhere. The limit exists. So we might be doing an IVT argument here. I see it's going to ask us for a mathematical argument. So first we're going to fill in some y coordinates and see how we can use those. So I'm just going to pause the video and do some calculations. You can do the same to find the y coordinate so that you're checking my arithmetic. You should always be able to check to make sure I haven't made arithmetic errors. All right, so what I notice is between 0 and 1, I don't know that there is an x-intercept. 0, by the way, is what we're looking for. Why am I saying x-intercept? Because the zeros of a function are its x-intercepts. So those are synonyms. We're looking to see whether it has a 0 or x-intercept. So between 0 and 1, the y-coordinates are 2 to 4. That doesn't actually prove that there is not a 0. It could cross the axis an infinite number of times, but it might go directly from 2 to 4. So we don't know whether there's an x-intercept there. But between 1 and 2, it goes from a positive y-coordinate to a negative y-coordinate. So certainly there must be at least one x-intercept between 1 and 2. So let's write our IVT argument. And I could say, I'm just trying to write this differently so you see some variety. We can apply IVT since polynomial functions are continuous over all reals. And now I'm going to show that our target y-coordinate is 0. So I'm going to show that I know that 0 fits between, and I'm going to turn this around, -18 and 4. And I like to show where those happened. So -18 happened when x was 2, and 4 happened when x was 1. So we know that because our target happens between two y-coordinates, then, or you might say thus, there is at least one real, and it doesn't have to be c all the time, I just choose c as a constant. There has to be at least one real number c, and now I'll use, instead of interval notation, I'll use that is an element of that curved e. So there has to be at least one real number c in the interval from 0 to 2, such that f of c is equal to our target y-coordinate. That happens to be 0. And here I've already mentioned IVT up above. So I've mentioned the theorem, I've mentioned continuity, I found a y target between two boundaries, and I showed my x boundaries, and I showed that there's at least one value c where f of c is equal to our target. So as long as you get those in some order. All right, moving on. How many zeros could this function have over all real numbers? So using our pre-calc, a cubic function, remember a cubic function, each x-intercept comes from a factor. So a cubic function can have 2 turning points and at most 3 x-intercepts. So f can have at most 3 zeros over all the reals. So if we know that there is at least one of them, between 1 and 2, what else can we come up with about this polynomial? Well, let's think about its left and right end behavior. Do you remember your pre-calc that the leading term tells you whether the graph rises or falls on the left and the right? So think about putting a positive, or as we go to infinity, put a very large positive into x, and these two terms become negligible. That's why we look at the leading term. So as x becomes a huge positive number, so when we cube a positive, it will stay positive, but then we're multiplying by -4. So our graph is going to fall on the right side. As x goes to negative infinity, think about putting a very negative number in. When we cube it, it will stay negative. When we multiply that by -4, it becomes positive. So we have determined that somewhere between 0 and 2, somewhere between 1 and 2. I think I have to fix I think I wanted to have this be in the interval from 1 to 2. Sorry. So somewhere between 1 and 2, we have just figured out that there has to be an x-intercept, because at 2, we're at -18, and at 1, we are at 4. So if the graph crosses here, how many other times could it cross? Well, could it actually cross all 3 times between 0 and 1 so that it gets back to a coordinate of 2 at 0? So let's stop and think about what are the possibilities here. Let me erase some of my scribbling so we look closely at this function again. I think you were taught in pre-calc, remember when you were doing synthetic division, to always think about +1 and -1. Here we can look at the signs of the function and be suspicious here. Do you see that if you put -1 in for x, this term would become +4, this would be -6 and +2. So we know that f of -1 is equal to 0. So we actually know more than this. So at -1 we get a 0. So where is our other 0? It has to, there has to be another 0 somewhere in between, because this is not a double root. So we kind of know the shape of our graph somehow or other. So we think that this graph is going to have 3 x-intercepts. We know approximately where 2 of them are. We know one of them is at -1. So our next step here is, now let's use our calculator. We haven't done this yet. Let's find the zeros using our TI-89. So I'm going to pause the video while I get the emulator visible here for you to see this process. So I've put our polynomial function. Oh, and I see an error. Let me go back up here. I don't know if we've seen this. F3 is the edit function. I have -4 cubed, and I didn't put in my x term. So I chose F3 to edit, and then left arrow. And let me get, here is where I want to insert my x. So F3 if you want to edit a function without retyping it. Okay, now I'm happier with it. The opposite of 4x cubed plus 6x plus 2. And we can go look at the graph, and I might have a strange window. I don't know what my window is set here. So it looks like we have 3 x-intercepts as we were expecting. You might decide here that you want to make your window narrower. So by going to F2, we could zoom in, or we could have gone to our window and put in specific values, and it looked pretty narrow here, so I'm going to have my x interval just go from -5 to +5. And I'm only doing that because it looked like it only took up half of the screen. And notice that my y min and y max were very low as well. So I might choose, these are just left over from the previous problem I had calculated. So I'll go from -5 to +5 there also, since what I'm really interested in when I go back to the graph is the zeros, the x-intercepts. So now I can see a little bit better where our x-intercepts are, and you could use trace to get close to them. F3 trace, we could simply move our cursor until it looks like we're getting close to the 0. But of course, there's got to be a better way than that, and it is to use the F5 Math menu. So under F5 Math, choice 2 will calculate zeros for us, but your calculator isn't very smart. So when you say find a 0, it's asking you which one. So you have to move your cursor to the left side, so you've got to give it a lower bound. So I get to the left side of my x-intercept and hit enter, and now it's asking to move to an upper bound. So I use the right cursor to get to the other side, and I hit enter. So now it's going to give me the x-intercept we had already figured out at -1. That's a 0. So at this x-coordinate, the y-coordinate is 0. And now I can go to the math menu again, F5, and I can choose 0 again. And this time I can do my lower bound for the next one, get to the left side, and then for the upper bound, use your right arrow to get on the other side of the x-intercept, and then it'll test until it finds it. And it's not going to give you the exact value, but it's close enough. We always need at least 3 decimal places of accuracy. And then if you want to do the last one, we knew it was between 1 and 2. So now I'm going to do choice 2 again to find the next 0. And I'm going to let the cursor move quickly to the left side, a little too far there. And hit enter for lower bound, and move to the right side of the intercept for an upper bound. And there's the 0 we were looking for between 1 and 2. Now notice here the y-coordinate doesn't really look like it's exactly 0, but this is as close as your calculator could come. So 4 times 10 to the -13th, close enough. We'll call that 0. So you can find the zeros using the F5 menu, and you have to always tell your calculator which 0 you're looking for by giving it a lower bound and an upper bound. All right, now we can return. And let's see what we have left. So you can transfer those answers onto your worksheet. I forgot to do that, but I'm not going to pause. You can go to the PDF file to get those. And now we want to make a continuity argument with a piecewise defined function. So we would like to find a value of c so that these functions, these pieces of this function, will pick up where they left off. So at x equals 4, we would like these values to pick up each of them where the other one left off. So from x going from less than 4 to greater than 4, we would like cx plus 2 to be equal to x squared minus cx plus 10. So what we really are saying here is that we want the limit as x goes to 4 from the left side to be equal to the limit as x goes to 4 from the plus side. So then the overall limit would exist, and for continuity we want that to be exactly equal to the value we get by direct substitution. So we want that to also be equal to f of 4 exactly. So we want these to be equal when x is equal to 4. So now I'm going to replace these x's with 4. So we'll have 4c plus 2, and you could have started with this right away. So this will become a 16 and a 10. So 26 minus 4c. And I can solve. 8c is equal to 24. C is 3. And then we could verify, or we could solve again here for one of these other combinations. So when we had 4c plus 2 equals 5c minus 1, we will get c is equal to 3. So we verified the constant we're looking for. So we could conclude that f of x is continuous at x equals 4 if c is equal to 3. And we're going to review the three-part definition of continuity. So we'll say f of x is continuous at x equals some value. Pick a or c, it doesn't matter what you pick. If f of a, well, let's say f is defined at a. If it's not, we could just quit. It has to have a limit as x goes to a. So the limit has to exist. And then the most important, the actual definition of continuity is, hey, if that limit exists, are we sure it isn't a pop point? So is the limit exactly what you get if you substitute a into the x coordinate? So you could start, if 3 is satisfied, remember that is the definition of continuity. So the first two parts are just to save you some time. If it's not defined and the limit doesn't exist, then why even bother testing part 3? All right, which parts of that definition are false at the given value of these? So here we can see that x has a whole, f of x has a whole at x equals 1. So it's not even defined. F is not, so part 1 is false. F is not defined at x equals 1. So why even bother testing the other two parts? This function, we know what this function is. At 7 we have a value of 1. And -1 over here. So we know we have a jump discontinuity. And again, part 1 fails. F is not defined at 1, or at 7, sorry. And the limit doesn't exist either. So it's certainly not continuous. Here we have a fourth root. So our domain here, we have to have under an even root, we have to have a domain at least 0. So our domain is x greater than or equal to 3. So x equals 3, our function is defined. And in fact, we know the fourth root is even lower than the square root graph. So we kind of know what this graph will look like. So is it continuous at x equals 3? It is defined. And does the limit exist? Well, remember at a closed endpoint, we only have to have a limit from the right-hand side here. So part 2, yes, it does have continuity because we only have to test the inside interval, so from the right-hand side. So part 3, is our limit the same as we get when we plug 3 into the function? So we would say that this is a continuous from the right side at x equals 3. So at an endpoint, it can't have continuity from both sides. All right, and our piecewise defined function here. Let's think what happens. We have when x is less than 2, we've got this piece of a line. So this is the point at 2, 3. When x is equal to 4, no, I'm sorry, when x is equal to 2, y is 4. And when x is greater than 2, we have a piece of a parabola. Let's put 2 in here by direct substitution, and we pick up at 3. So we get a piece of a parabola there that picks up. So we've got a removable discontinuity when we graph this. So let's think about it. Test 1, part 1, is it defined at x equals 2? Yes. F is defined at 2. So that part is true. Part 2, does the limit exist? The limit as x approaches 2 of f of x does exist, and it happens to be equal to 3. But part 3 is false. Part 3 is where it fails, because the limit as x approaches 2, limit as x approaches 2 is not equal to f of 2, which happens to be 4. So here we know 3 is not equal to 4. The limit was 3, and the actual value of f of 2 is 4. So we know that part 3 is false. All right, well, that video got to be a little long, but we made it through.